This video is going to introduce a process called primary drainage, and it's going to introduce the concept, not of capillary pressure, which we've met before, but capillary pressure plotted as a function of saturation. So let's just define the processes first. It's called primary drainage. And what we're going to look at here is it's primary because we're going to assume that we have a porous medium that's initially entirely saturated with a wetting phase, which in this case is going to be phase 1. Drainage is defined as the displacement of a wetting phase by the non-wetting phase. So we're going to assume for this discussion that the phase that is being injected or moving into the porous medium is non-wetting, and there's the wetting phase originally present, and we'll call the other phase phase 2. So phase 2 will be displacing phase 1, and it's primary, fully saturated with phase 1, drainage, phase 2 is non-wetting, phase 1 is wetting. So what's the classic example? The classic example would be a porous medium full of water, and I inject CO2 or hydrogen for storage purposes. The other classic example is where hydrocarbon originally moves into porous rock to form an oil reservoir or a gas field. Okay. Now we're going to see where this pore and throat idea of a porous medium comes into itself. So I'm going to just draw schematically, and I'm not assuming that really porous media are so regular and easy. Here are our pores. Yes, in reality, it's a complex three-dimensional porous medium. But I'm just going to draw this for illustrative purposes. And then we have the restrictions, the throats between them. So going back to a previous video, we've defined now precisely what we mean by pores and throats. And so this is a region of the pore space, and I'm going to do it quickly. Okay, so this is a pore, and this is a throat. And yes, I know I said a throat was a surface mathematically, and now I'm drawing it as some sort of tube. It's not literally a tube, but it is the narrowest region, and that's going to turn out to be very significant. So imagine that this is entirely filled with phase 1. I'm not going to waste time just drawing it all out in blue. And now I'm going to inject phase 2 from here. And the way in which you can think about it is in terms of pressure. So I'll draw the pressure here. So imagine this is pressure. Okay. We're going to start with the pressure in phase 2 equal to the pressure in phase 1. So the capillary pressure is equal to 0. There's no pressure difference. And then what I'm going to do is I'm going to increase the pressure in phase 2 while keeping the pressure in phase 1 constant. So I'm going to increase the pressure. Okay. Now let's look at what's going to happen. I've got here at the inlet throats of different size. Now, I've defined a throat as a surface. I said you could define the radius, the inscribed radius there. Roughly speaking, it isn't precise, but we know that if it's a circular tube, the capillary pressure, P2 minus P1, that is necessary for phase 2 to displace phase 1, at least in a circular tube, is given by 2 times the interfacial tension times the cosine, and here it's the receding angle because phase 1 is receding, and then it's divided by the radius, and in this case this is the radius of the throat. Okay, so RT. So roughly speaking, that is actually the capillary pressure, the pressure difference between the phases necessary for phase 2 to displace phase 1. Okay, so what's going to happen? Well, as I increase the pressure in phase 2, it's going to invade first the widest throat, because the widest throat, illustrated here, is the one with the lowest pressure. So imagine it's here. That's when I'm going to fill. Now that pressure is also possible to fill the pore, because the pore by definition is wider. So I fill the widest throat, I then fill this pore. Now I've got to increase the pressure a bit more because there are no other wider throats. So what am I going to do? Refill the next widest throat. And of course, this isn't the world's most accurate diagram. I did it very quickly, but any heterogeneous real medium is going to have throats and pores of all different size. Say this is the next one. So it fills that one, then it fills this. And then maybe this is wider, so it's going to fill here, and then it fills here. And then maybe this is wider, and then it can fill here. Oh, this is a really wide one, and then it always fills the pore. Then maybe we're not quite there, so we need to increase the pressure a little bit more. Okay, we increase the pressure here, and now at this point it can fill here, 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 here. Oh, and now it's gone from one end to the next. Okay, so that's primary drainage. What we're doing is we're simply filling the widest available throat. What I mean by an available throat is a throat at the inlet or any throat next to a filled pore, but I can't fill this throat, even though it's the widest throat of all, because how can the gas or the oil get there? It can't sort of beam itself into the pore space, can it? So it can only go there if it's connected to the inlet. So if there's a connected path to the inlet, then it will fill. So if you're always filling, you fill the largest available, right? And available means connected to the inlet, available throat, and then plus any adjoining pores, because the pores are always larger, right, than the throat by definition. Now this process, as a physics-based process, so among physicists, has been called invasion percolation. It's invasion because one phase is displacing the other, it's pushing it out, and it's called percolation because essentially you're filling more or less randomly. Well, you're not filling randomly, you're filling randomly in space, but in a specific order in terms of size. Now, I'm not going to develop that idea now. I will describe percolation precisely in a later video. But just for the record, the physical process of primary drainage is an invasion percolation process. And I will describe, as I say, later what both words mean. You know, invasion, it's basically this advance, and I will describe in more detail what percolation means. Okay, so it's an invasion percolation process. Then as I continue, right, this is the pressure at which I first span the system. I go from one end to the next, okay? And this pressure is called the entry pressure. Now, sometimes you might say, well, that's not the entry pressure. Surely the entry pressure was the pressure to sort of first get in rather than get across. Yes, you can say that, but the problem is, you know, I got a piece of rock and I sort of chipped it, so there's a really super wide throat to begin with. So it looks like the entry pressure is very small, and you haven't got anywhere. So in terms of flow, we want to know when a phase can move through the porous medium. Actually, strictly speaking, the entry pressure should be when you first, well, the technical word is percolate, by which I mean there is a connected path. So P entry here is when there is a connected path through the medium and this is of phase 2. Okay. Now what happens? Well, I'm going to use a different colour just to illustrate this, but displacement continues, Obviously, this is an infinite porous medium, and we keep going. Well, it keeps going and keeps going. But locally, we keep building up the pressure. So maybe the next one is here, and it fills here, and then it can fill here and here. And we've built up the pressure now. Okay, and then we keep increasing the pressure. What do you think will come next? Say here, right? The flow can apparently go backwards, and then, aha, this is that super wide pore, so it likes this. So we built up the pressure here, and now we filled more regions. So eventually we keep going. And we eventually do saturate all the pores and throats, right? Eventually we're going to go everywhere. So I'm not going to do this in too much detail. Okay, we eventually fill the entire pore space. Is that right? Yes, but with a subtlety. Imagine what I said about in cross-section. What do these pores and throats look like in cross-section? They're very irregular, but I describe them as triangles. So what happens, and now I've blown up the triangle, so imagine this is an expanded description. Yes, phase 2 goes into the pore space, and we've already described this now, okay, and I showed it in a previous video. Phase 2 goes into the pore space like this, okay. So this is phase 2. Here we have water, which is phase 1. As the pressure continues, the capillary pressure continues to increase, okay, keep moving up, filling narrower and narrower and narrower regions of the pore space. In a throat or a pore where phase 2 is already present, the capillary pressure increases, the curvature increases, the radius of curvature decreases, and what happens is phase 2 pushes further and further into the corners, and in fact sometimes can disappear altogether. So what happens is over time, these menisci move further and further into the corners of the pore space. But there is still phase 1, the wetting phase, present in the corners. In general, that's not just the corners of the pore space, it's the corners and roughness, okay? So as the capillary pressure increases, you get pushed more into the corners as the capillary pressure increases, but there is still some water present. And that's important because you might say, well, I don't see how this throat, for instance, could be filled from both sides because the water has to escape. Phase 1 has to escape, but it can move in from both sides and the water is escaping through the corners. So our conceptualization of a porous medium in terms of pores and throats, we have this invasion percolation process. You always fill the largest available throat, and you keep doing this. In fact, if you keep increasing the pressure and keep increasing the pressure, you can fill essentially the entire network, but the water here can escape through the corners, and as the capillary pressure increases, the water is forced more and more and more into the corners. Now, there are some subtleties here. There can be some regions where genuinely these layers, these wetting layers, do not connect, and so water can be trapped. But as a simplification, this is a perfectly reasonable and, in fact, a reasonable quantitative explanation. Now, the final thing. Capillary pressure. Well, just defined it. But now let's do something else. We can write the capillary pressure here, not as a function of contact angle and radius, but in an average sense. So I got a piece of rock. I impose a pressure difference between the two phases. Phase 2 goes into the rock. I can define the saturation as the fraction of the pore space occupied by one of the phases. And clearly, if I'm looking at phase 2, as the capillary pressure goes up, more and more and more of the pore space is occupied by phase 2. Traditionally, we sort of do it the other way around. PC is P2 minus P1. But the saturation that I plot here is the saturation of phase 1. Just the same way as we measure contact angle through phase 1, we generally plot everything as a function of the saturation of phase 1. And by default, that's the water saturation, the wetting phase saturation. The lowest it can be is 0 if there's no water present. Initially, it's 100% water. The saturation is 1. let's just draw schematically what this might look like. So the capillary pressure tends to have this form, that strictly speaking, the entry pressure, if I make this a larger and larger system, we sort of basically have to go up and then it enters. But where it first goes through the entire system is normally at a very low saturation of phase 1, in fact. And this is your entry pressure. Okay. And then, generally speaking, we will have some water trapped, or you don't go to an infinite pressure. So we have some remaining or connate saturation. So we can call this SW1R. We can call it SW1I because it's actually the initial saturation from which we then inject water. We can sometimes use this word connate. It's a rather archaic word used in the oil industry. It simply means what you find originally. So actually I'm going to call it S1I. We stop at some capillary pressure, some maximum value, and this is the water that remains. And you never get every last molecule of water out. Let's think of some typical numbers so that we have, some idea of where we are. So often this effective receding contact angle is close to 0, so the cosine is close to 1. If we have, for instance, carbon dioxide and water deep underground at typical sort of reservoir type conditions, so say 1,000 meters below ground, temperatures around 50 or 60 degrees C, the interfacial tension here is not 70 millinewtons per meter, but often a little bit lower, say 50 millinewtons per meter. 2 times 50 is 100. So this 2 sigma here, right, if I just want to get order of magnitude, right, this 2 sigma is 100 millinewtons per meter. That's 0.1 in strict SI, newtons per meter. Cos theta, I just said, is approximately 1. And then imagine a typical throat radius, say, a sort of mid-range, so when we're sort of about halfway through, is say 10 microns. Right, that would be quite a permeable rock, right, one that allows flow by reservoir standards quite easily. So 10 microns, again, strict SI, 10 to the minus 5 meters, and this is newtons per meter. So that's going to give a P2 minus P1, so your PC here is 0.1 over 10 to the minus 5, that's 10 to the 4 pascals. So something around here, right, maybe typically 10 kilopascals. Now remember here with pressure and everything else, if you ask me, you stick to strict, rigorous, no holds barred SI, right? Don't try and do clever things. Bare SI, then you can put the kilo and the megas or the whatever you like. So capillary pressures are normally for rocks in the sort of kilopascal, tens of kilopascal range. So just to finish here, let's imagine the pore sizes are smaller. Imagine we have a rock that is tighter, doesn't allow flows so readily. Well, obviously the capillary pressure will be higher, won't it? So if we had typical pore sizes 1 micron, the capillary pressure would be 10 times higher because typical capillary pressures go as 1 over R. So if we have smaller throats, the capillary pressure will go up. Now let's think of something else. Imagine we have a very wide range of throat size. So if I have these sorts of rocks, they're sort of atypical throat size, and many of the throats are around that size, and so you get quite a flat-looking capillary pressure curve. If, on the other hand, we have a more heterogeneous rock, we have a much wider range, so we can have some big pores that we enter with, and then some small pores that we take ages to access. So something like this would be a more heterogeneous rock. And what I mean by this is a wide range of throat craters. Okay. So that concludes this video. The main concepts are the idea of a displacement, one thing pushing out another, the sequence in which it's done for primary drainage, This is simply invading the largest available throat, and then the pores automatically get filled next. This then leads to a capillary pressure function, which we normally write as a function of the saturation of phase 1, the water saturation. And then we get some idea of magnitudes here and what happens if we make things smaller, bigger, more heterogeneous. Thank you very much.